Hi everyone, welcome to Chapter 10 about electrolyte solutions. Here's your reading for this chapter. And I'd just like to start off by saying I'm kind of excited to be doing this chapter. It's the first time I've done it for this class because it didn't fit so well in previous years, but I've cut out some of the subjects I used to talk about, and I figured I'd put this in. It's a little closer to what my research is, and what's nice about this chapter is to this point, we've been dealing with a lot of fairly vague concepts like activities and fugacities and activity coefficients. And in this chapter, we finally get to see some real examples of how to apply these fairly vague theories. So with that in mind, we'll forge ahead and see how it goes. Here's what we'll be talking about today. We'll get a chance to calculate the free energy to solvate an ion. Then we'll see the chemical potentials and activity coefficients for electrolyte solutions, and we'll see how to calculate those specifically using the Debye-Huckel theory. Then we'll apply that to equilibrium type problems, and hopefully we'll get to do a sample problem there. On this slide, I lay out a number of assumptions that we're likely to make about this chapter. We will make additional assumptions as we go besides these, but these are a few overarching ones to keep in mind. It's worth also noting that the theories in this chapter are some of the more basic ones. And by basic, I mean relatively easier to understand. However, they do make fairly drastic assumptions and they have relatively low accuracy compared to a lot of other theories that are out there but are far more complicated and difficult to understand. So if you go on to graduate school in this subject or a similar subject, you may have a chance to learn about those more complicated ones, but for now, these should provide a good starting point. The theories I'll be presenting to you apply best for very low dilutions of electrolyte solutions. As we get more and more concentrated, the theories will diverge from experiment. We're often going to assume complete dissociation of the ions in the electrolytes, so that makes it a strong electrolyte, and we'll get to the other assumptions as we go. Do you remember the joke I told you a few weeks ago about the spherical cow? Yeah. That joke definitely applies to this chapter. We're going to be making a lot of spherical cow type approximations. Okay, in this section of the book, it touches on something that I find highly interesting personally because it's a problem that I'm constantly struggling with in my research, and that is to accurately predict the free energy of solvation. What's the free energy of dissolving something in water or another solvent? And an ideal starting place for a theory of this sort is called the Born model. And Born was a scientist who lived about 100 years ago and was very involved in the development of quantum mechanics and other areas of physics and chemistry. He was a German scientist, and his name was Max Born. So the question that the Born model answers is what's the free energy for the following reaction? We've got an ion just existing in the gaseous state, so it's a vaporized ion. And then what's the free energy of solvating it in water, for instance? We'll just use water as the solvent of choice. So I'm going to depict that ion right now. There's the ion. I'm assuming it's spherical, okay? And we'll call this the solute. All right? And it's, like I said, a spherical ion in a vacuum. Because in the gas state, we can assume that it's essentially in a vacuum. It's going to be very far away from any other particle. Okay? I'm going to define a few variables here. Big Q is going to be the charge of the particle. Then another variable, Z, is going to be the number of protons minus the number of electrons. So that's going to equal that's going to be related to what charge the ion has. And then the variable little e, this is not e raised to the power of x, or Euler's number. This is the proton charge. And you can find that constant in the front of your book. Notice that the charge of this ion is going to be equal to the excess number of protons that we have multiplied times that proton charge. Okay? Then we also have the radius of the ion. Okay, so next we have to consider the solvent. What are the solvent molecules going to be like? We're going to make a very simple model of the solvent. We're going to assume that it is what is called a dipole. Now, water molecules, as you know, are a dipole, but instead of 2 hydrogens and 1 oxygen, we're just going to represent this by a bar with partial charges on either side of it. And then we're going to assume that this is a very small length between these two charges, an infinitesimal length. Okay, so now with these assumptions in mind, we can now ask, what is the energy to solvate the ion? And by that I mean surround it with solvent molecules. So this is the situation that we're considering here. So we have the solute sitting alone in the middle of a vacuum in the gas state. And we also have a system of a whole bunch of those little dipoles. And notice they're all kind of scattered around randomly, pointing in random different directions like that. So here's the solvent. What's the energy of bringing that ion into the middle of that solvent in order to make a solution? So now I'm going to depict those solvent molecules. Out here far away from the ion, they still have fairly random arrangements, but up close to the ion, they're going to arrange themselves according to that charge. And so hopefully you can see that not only is the potential energy of this interaction changing and the enthalpy, then that means the enthalpy, but the solvent is losing some entropy. That there's going to be an entropic cost to put that ion in the middle of that solution, because those ions are those solvent molecules are spontaneously arranging themselves. Okay? So there's going to be both an enthalpic and entropic cost associated with this. So here is the equation that Born figured out. And this equation is too advanced for me to tell you where it comes from in this class. However, if you ever take an electrodynamics class in graduate school or in some other context, then you'll probably learn where this comes from. But I'm just giving you the result from on high, so to speak. So there's those excess number of protons, then times the charge of the proton, both of those are squared. Then we have Avogadro's number, and then 8 pi. Then we have this epsilon 0 times the radius of the ion, 1 over epsilon minus 1. Okay, let me explain what some of these other constants are. This epsilon naught is a universal constant, and you can find the value in the front of your book. It's called the permittivity of a vacuum. And what is that one? That constant tells you that if you have two charges separated by a certain distance, what's the force that those charges feel? Then this epsilon, without the naught, is called the dielectric constant. So if this is a universal constant, this one is a material specific constant. So it depends on whatever the solvent is in this case. And for water, at standard state, this epsilon is approximately equal to 78. And what it represents is the size of the water molecule and its capability to turn around and like spin in place in response to a charge. Okay? So, like I said, this is a very low-level theory. This is like it's a good starting point, though it's still going to be fairly inaccurate. But what are some possibilities for improvements that we could make? Well, for one thing, this model assumes that the water molecules, solvent molecules, rather, don't adjust to each other. Okay, so this is a little bit strange, but those solvent molecules only feel the ion. They actually don't feel each other, which is definitely a suboptimal approach. The next one is the density. So the Born model is making the assumption that if we have the distance from ion, and then over here we have the solvent density, then right here at R, the Born model assumes that the density of the solvent is 0,0,0,0,0 inside the ion, and then it abruptly jumps up, and then it stays constant like that forever. It assumes that there's no variation whatsoever in the density. But in reality, the way that solvents actually look around a solute, this is the same thing, distance from ion center. Over here we have density. Then it's 0 inside the ion, but then it will jump up like this and then actually kind of oscillate like this. That's how the density around an ion actually looks. And that's because that ion is pulling in a solvation shell of water molecules and pulling it tight. And then those water molecules actually prevent other water molecules from getting too close, and so that lowers the density at a certain point. But then outside those, more water molecules are attracted, so you get a series of solvation shells outside of that ion. And the Born model doesn't account for that. A better model would account for that particular phenomenon.